Okay, I think we are live now.
Okay.
Okay. Yeah.
So I'll be giving you two questions, and if time permits, we'll move on to a third question. If time permits, okay?
Okay.
Hmm. Okay. So see, first question is you are given a linked list. I'm just
Okay.
giving you a linked list, and I'm trying to make you understand the question.
Okay.
Sorry.
We are given a linked list. Yeah, I'm drawing it as well on the paper.
Okay.
Yeah. Yeah.
So this is a linked list given to us. It is 1, 2, 3, 4, and after five, five's next pointer is pointing to null. Okay.
Okay.
So this is a linked list given to us, head of a linked list. Okay.
Okay.
Now we have to return a linked list with first node is this one, second node is the last one. Okay. So
Okay.
five will come over here.
Okay.
Okay. You get it?
Okay. I got it.
And then this two, then four, and then three. You get the question. Should I take some other or I take some other example?
Okay. No, no, I got it. So like
Oh,
the linked list is 1, 2, 3, 4, 5. So
yes.
my resultant linked list should be 1, 5, then 2.
Hmm.
After that 4. After that 4.
And
Yeah.
three.
Okay. After that 4 and after that 3. Okay. Hmm.
Hmm.
Okay. So like it seems like first one, then the last one, then then the
Second, then
second,
second last.
second last, and at the last we will have the middle one.
Yes.
Okay. Let's say I have a list of 6 elements, suppose. So
Just give me just 1 second. Uh, can you see my screen? I
yes,
mean, what are you seeing?
yeah, I can see your screen. I can see meat.
Meet. Okay, take
Yeah.
care. Fine.
Yeah. Okay, let's say I
Go
have
ahead.
linked list with 6 elements.
Hmm.
So then my resultant list would be 1, 6, 2, then 5, 3, 5, 3, and then 4. Okay, okay. So what I can see is that okay, so first and last, then second, and then second last, and so
Hmm.
on. It's going on. So, what I can do is um, I can reverse the half of the list, like
Hmm.
the right hand side of the list. So it would look something like this. Like, um, can I show my screen? Okay.
Yes. So should I stop presenting my screen?
Yeah, sure.
Oh.
Okay. So like um, one, one, two,
Hmm.
then there is 3, 4, 5. Okay, so these are the elements, 6 as well, and after that there is null.
Okay.
So what I would try to do is I would try to reverse the right hand side of the list.
Hmm.
That would be something like something like this. So 3, and after that um, okay, after that I will do 4, and from here it will be in reverse. So 5 will be pointing to this, and 6 will be pointing to this, and okay, so this is good, and 4 will be pointing to null. Okay, yeah, that should might work. So 4 will be pointing to null. Okay, so what I will do after that is Um, I will have two pointers.
Hmm.
First will be over here. So PTR1 would be at 1 at this
Okay.
point, and uh, over here at 6 PTR2 will be there.
Right.
Okay. So what I'll do, I'll create another list. Okay. No, no, no. I will not create another list. Let's take two counters as well. Like this pointer will point to 1 and this PTR2 will point to 6. Let's take P1 and P2 as well, which will be initially pointing to null. And yeah, okay. So there will be P1, which will be equal to null, as well as P2, which will be equal to null
Hmm.
at starting. So what I want to do is one should point to 6, right? So PTR1 should point to PTR2,
Hmm.
but before that, like I okay, like I have to move PTR2 forward to 5. Like PTR2 is pointing to 6, it should point to 5 before me assigning PTR1's next as 6. So what I mean is I will do PTR2 here and P2 over here. So
Okay.
what I'll do, I will say PTR once next as P2,
Okay.
and yeah, okay. So this will be done. PTR once next will be P2, and
Okay.
after that I will do PTR one. Okay, but I have to keep check of the second one as well because I will lose the reference to the two, right?
Hmm.
Yeah, I will lose reference to two. So okay, so P1 initially will be pointing to PTR1's next. Okay, P1 will be like P1 won't be null. P1 would be pointing to 2. So P1 would be pointing to 2. So after
Hmm.
I have done P1's next as P2, I will do P1 is equals to P, and
Hmm.
P is equals to P1 PTR1 dot next.
Hmm.
So yeah, okay. Yeah, yeah. Yeah. So like the list would become one would be pointing to 6, and yeah, so one would be pointing to 6, and at this point of time, my PTR one is at 2, and my P1 is at 3, and my PTR two my PTR2 is actually at 5, and my P2 is currently at 6. So after this is done, I have to do one more step. Like I have to do that PTR2 should be equal to PTR2's next, and P2 is equals to PTR2. Right? You got what I'm saying?
Yes.
Okay. Okay. So first I have to like reverse the half of the linked list,
Hmm.
and after that I will have two pointers. So the reverse part of the list will have a specific head, let's say PTR2, and the left hand part will have PTR1 as the head, and I will just create a new list. Won't be a new list. Actually, will be changing the next part of the node.
So what do you think this will work?
I think, yeah,
Okay.
yeah. Wouldn't it?
Stop logging. Okay.
Yeah,
So what will happen is your one will point to five, your two, sorry, your one will point to six,
yeah.
okay, your two will point to five, your three will point to four. Eventually it will happen. But what should happen is your resultant linked list should be 1, 6, 2, 5, and 3, 4. Write it down.
Okay, okay, yeah, I got it. So like I have to point. Okay, okay, yeah, 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 yeah,
You should point 6 to 2 as well, and
yeah.
then
Right,
5
right, right,
to 3 as well.
right. Yeah. So one is
And this
pointing
will
to.
not happen in something that you are suggesting.
Okay, so like the reversal part, that that is not correct, or
Hmm.
is it like is it correct, or um,
It is correct, but you have to look for, you have to connect
right?
all the things. You are
Okay,
not
okay, yeah, yeah,
connecting
yeah,
everything.
yeah, yeah, I got it. So like okay, so this part that I've done is something wrong. So at reversal, after reversal, let's say I have PTR1 and PTR2 at last indices, like the heads of two linked lists that I've created. Uh, One is reversed one and another one is the plain one that was given earlier. So, okay, so like one should point to six and then six should point to two, right?
Yes.
Yeah. So like I would require P1 and P2 as well. Like P1 and P2 would be required to get this done. So one should point to six, right? Hmm, right. So I have to keep check of five. I have to keep five and two as well. Like I have to store the references of five and two because I need them afterwards as well. So okay. So one PTR one and PTR two. Okay. So let's take that P1 is pointing to two and P2 is pointing to five. Let's take something like that. And okay, yeah. So now what I am doing, now what I will do, first of all, I will have PTR one dot next as PTR two. That way I will have one to be pointing to six. Yeah. And
Hmm.
after that, PTR2 is still at 6, so I will do PTR2 should be pointing to P1. So
Yes.
that way, now 1 will be pointing to 6 and 6 will be pointing to 2, right?
Yes.
Okay. So when this is done, I want 2 to be pointing to the last element of that particular thing, right? So it should be pointing to 5,
Hmm.
right? Um, okay, okay. So now what I will do, this is my P1, right? This is
Hmm.
P1. So I will just simply do PTR1 is equals to PTR1 is equals to P1 and P1 is equals to P1 dot next. P1 dot next. Okay, so that
Hmm.
way PTR is now at 2. PTR1 is at 2 now. So PTR1 is at 2 and P1 is at 3. Is at 3. Yeah.
Yes.
So now I have to point, I have to do what? I have to um, okay, PTR2 becomes PTR. Sorry, okay, this is okay. This is good. Okay, PTR2 should be pointing to so PTR dot next is equals to P1. Hmm. So at this point of time, I have done with this. I have to do something over here so that next time when the loop runs, so this will be in a loop. So while something gets while PTR one or PTR one is not equal to null or PTR two is not equal to sorry I should have and over here and PTR2 is not equal to null. So this will be a loop and just before another iteration what I'll do is what I'll do okay I will do PTR okay first of all P2 dot next is equal to sorry P2 is equals to so that way I will lose PTR okay so PTR2 is equals to P2 and P2 is equals to P2 dot next. So, so that way my P2 will become 4 and my PTR2 will become 5. then next time when the loop will run, next time when the loop will run, ptr1 dot next. So ptr1 is 2. So 2 will be pointing to 2 will be pointing to ptr2. Ptr2 is 5. So 5 will come over here. And yeah, yeah. So now okay, ptr2. So 2 is pointing to 5. Then ptr2's next will be equal to p1. So ptr2, that is 5. 5's next will be 3. 5's next will be 3. Yeah. And 5's next become 3. Then again this thing will happen, and 2 will become 3. 3 will become 4, and p2 will become null at this point of time, and p2 will become 4 again. Okay. So I have to see over here, this thing might be okay. Okay, so this happened, and ptr1's next will be equal to ptr2. ptr1's next, that is 3, will be equal to ptr2. Ptr2 is actually equal to 4, and ptr2's next will be equal to p1. So this is something that I have to look, that at the end my 4 will be pointing to again 4, like its next would be equal to itself. So that I have to keep keep a check of that, I think. So over here, my if my ptr2 is equal to p1, if my ptr2 is equal to p1, then then I have to do ptr2's next is equal to null. Ptr2 dot next is equal to null, right? Else I
Hmm.
will do this.
Okay.
Okay. So I think this will just work. There is a possibility, like I don't know if no, there won't be a possibility that PTR1 should be pointing to PTR itself. So PTR1 and PTR2 won't be equal. Yeah, I don't think they will be equal ever. Okay.
Okay.
Yeah, I think this will work.
So what will be the complexity of this solution?
Okay, so like first of all, I have to reverse the linked list, and for that I have to first get to the middle part. Like I have to get the middle node and the last node. So to get the middle and last node, it will take O of n time. So I will have two pointers, like slow and fast pointer, to get to the middle and the last element. And when I will get middle and last, I will reverse it, and reversing will take. Okay, reversing would also take O of n time, and and this one will also be taking O of n time. Yeah. So the complexity would be O of n plus n plus n. That will be O of n.
Hmm. Or space complexity?
Space complexity would be constant. It will be constant because I'm not using another any space over here. Like those nodes, I'm just changing the next part of the particular node.
So you're confident with this solution you have given to me?
Yeah,
Okay.
I think so. Yeah, yeah, this will work.
Okay. So you took about 15 minutes to solve this question. Just telling you, there's nothing
Okay.
to do with this question. Okay.
Yeah.
So the next question is, you just open your notepad.
Okay. So does this will it work?
It seems that
Okay.
it will work.
Okay.
Okay. So your next question is, you have given a tree, binary tree. Okay.
Okay.
And then you have to give me in order of the tree.
Okay.
Yes.
Just the in order.
Yes.
Okay.
Don't. Okay.
Okay
Do
then. Yeah.
this under this.
Okay. So like let me just get it out of sight. Okay. So we are just given a tree, and we just have to
Yes.
return the in order.
Yes. In order of the tree.
Okay. So like storing like as a string or in a list.
Whatever you want.
Okay, so like in order, let's say I have a tree like one. Okay, okay. So in order means left, root, and right. So can I just directly print it? So that okay, fine. So void in order. I'm just writing the function directly.
Hmm.
Okay. So there is a node, root node, and let's take a array list of um, array list of node, and that will be called as in order. In order. Okay, in fine. And what I will do, I first have to take the left part, like I have to go to left. So um, I will just I will just have if first of all like the base condition, if root is equal to null, I will just return, and after that I will go to the left part, that will be in order root dot left, and with in over here, and then I have to add that particular element to the list. So I will have in dot add the root, and again in order for right, root dot right. Okay, root dot right, and in. So yeah, that's the in order of a tree.
Okay, so I want you to do the same question, but iteratively.
Okay, same question but iteratively. Okay, so okay, can I use a stack?
Yes.
Okay, okay. So okay, so what I'll do in this particular function, like the conditions. Okay, let's just do it over here. Okay, so I'll take a stack of root, or sorry, stack of node, that I'll call just stack is equals to new stack, and okay, so like okay, so there is a stack with me, and I'm at my first root node, so I'll add that particular node to the stack. So the first node, the root node, will be in the stack. After that, I'll go to the left and add two to the stack. Then I found out null. I will return. I will pop out two. Yeah. Okay. Okay. So like, um, I'll just keep on adding the elements first of all. Yeah. So I'll add stack dot add root first of all in the stack. Okay. Yeah. Like I have to go to root dot left and right. I have to pop out two and store it in the PTR. Okay. Okay. Let's do something like this. There is in. So in I will add the popped out one. Add a popped out one and go to the left part. Okay. Okay. Hmm. So I'll take a node node pointer which is at starting is equal to root. So ptr is equals to root, as ptr is over here, then okay, I have a stack, I've added root in the stack. Okay, I've added root in the root
Can
is
you tell me what you are thinking so as to know if we are on the same page?
okay, uh, like what I'm thinking is that uh, there is, let's say these are a few nodes in the tree. So this is one, this is two, this is three. Sorry for the handwriting, and this is four, five. Okay. So what I'm thinking that the root is this node. So in the stack, first of all, what I'll do. So in the stack, what I'll do is I will push one at the very beginning and go to the left part. I found out that I got two. I'll push two over here. Then I'll say like there will be a PTR, like there will be a pointer that is pointing to these nodes. So like PTR is first equal to root. So PTR is not actually equal to null. So I added it to the stack. Then what I did, PTR is equals to PTR dot left. So over here, PTR's left is 2. That is again not equal to null. So I added it to the stack. Then I will again go to the left part, which is null actually. So if it is null, I will pop out this element, and after popping it out, I will add it to the list. So in order would be like 2. So in order is starting from 2. Now when I popped out 2, I'll go to the right hand side. If the right hand side again, so PTR is again equal to null. So I will move back, but like move back means again it is null. So I will pop out another element from the stack, that is 1. So I popped out another element from the stack, and okay, so I added it to the in order traversal. So one is added to the in order traversal. Now when I popped out and added it to the in order, I will move to the right subtree of 1 and again do the same. So now stack is empty, but now stack is empty. I will do what? I will add 3. I'll add 3 and go to the left hand side. 4, I've added 4. I've added 4. I try to move to the left part of the 4, it becomes null. So I'll pop out 4 and add it to the in order traversal. After that, I try to go to the right part of the 4, which is again null. So I'll pop out again, that is 3. I popped out 3, and now I will move to the right hand side of the 3, right hand side of 3, that is 5. So I added up 5 over here in the stack. I found out that the left hand side is null. I popped out this element, and this is my in order traversal.
Okay.
Yeah.
So why have you chosen stack? Why not Q or some other data structure?
um, like this is a depth first search traversal. So in order to get to the depth first search, I will be using stack. Like I used recursion over here. So correspondingly to replicate recursion, I must use a stack, because internally recursion also uses a stack.
Okay, go
Yeah.
ahead.
Okay.
You can write the code now.
Okay, so there will be definitely going to be a loop while okay, but the stack can get empty. The stack can get empty. Okay. Okay, let's see the condition afterwards, and let's try to complain that I've added root to the stack. That is, okay, one is added to the stack. What I'll do, first of all, I'll go to the left hand side of the that. So if PTR is not equal to null, if PTR is not equal to null, I'll go to ptr is not equal to null, I'll go to the left hand side of the that particular. So ptr would be equal to ptr dot left. Ptr dot left. Okay. And when I have like ptr is equals to ptr dot left, first of all, I've added root, so I won't require to add it again. Let's do one thing. Let's add this over here. Instead of root, let's have ptr. I've added ptr to the stack and moved to the left hand side of the tree. So ptr is equals to ptr dot left. Now I'm on second. Now now ptr is equals to ptr dot left. Okay. Hmm. Okay, so I'll again the loop will run and PTR's left would be equal to null. So if PTR is equal to null, if PTR is equal to null, I will do one thing, that is stack dot pop stack dot pop, and I'll add it to the list. So I'll add it to the list. So list is in dot add add stack dot pop. I'll pop out the topmost element from the stack and push it into the array. So array list. Okay, now two is added to the list. Okay. Okay, now two is added to the list. So when I have when I have popped it out and added it to the list, I have to do, okay, I have popped out two. So I have to store it here. So I have to store it. Okay, let's store it. Node is equal to stack dot pop, and add it to the list in dot add node to the list, and then ptr is equals to node dot write. Okay. Now okay, I got it now. Now it is null. I will again pop it out, and when popping it out, I will get one, and I will go to the right hand side of one. Okay, but I have to see this condition, like the stack might get empty. Okay, so ptr's right is actually equal to, okay, okay. So in starting it is containing only one. After that, it is having ptr dot add. Let's just remove this one. Ptr is added. One is added to the stack, and I got two. I got null. Null. When I got null, I popped out two. When I popped out two, I go to the right part. I had ptr equals to node dot write. So ptr is again equals to null. I popped out one. I popped out one. ptr is now equal to, okay, 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 okay. So okay, I think this stack dot is empty. This will work. If stack is not empty, just keep on doing it. When the stack becomes empty, just stop doing this. Okay, I think this will work. I can't hear you.
What will be the space complexity and time complexity of the solution?
Okay, so the space complexity would be O of n. Yeah, O of n, and the time complexity would be again O of n, because we are just traversing each node once, I think.
Okay.
Yeah.
So we are still left with 30 more minutes. So should we go ahead with another question?
Yeah, we can get to the third question as well.
So okay, next question is, you're given a tree again,
Yeah.
okay,
Okay.
and then you have to tell me if this tree is a binary search tree or not.
If that tree is binary search tree or not.
Hmm.
Okay. Yeah. Yeah. Um, just a second. Okay. So, like, we have to check that the tree is binary search tree or not. Okay. So that's pretty simple, I think. Like, if the binary search, I just have to check for each node that its left node and right node is um, the left and right node. Like the left node is smaller than the node than the root node, and okay, no, but I have to check for the whole subtree. Okay,
Yes.
yeah, okay. So like I have five, four, six, three, two. Okay. So for each node, I have to check that all the nodes on the left subtree are smaller than the node that particular node. Right? So like what I can do an in-order traversal. I can do an in-order traversal. I can go to the leftmost part, and from that particular point, I can check that the element at the top is actually greater than the leftmost part, and uh, like what I'm thinking is something that for a tree I will go to the leftmost part, and at that point at that node I'll check that its parent is actually greater than the that particular node. I'm at the leftmost part of the tree, and this particular node, I'll just take it to the parent that the parent is greater than the node. Then, when I will get to the right part of the tree, I'll check uh, that the right part is actually greater than the parent, and I will keep coming up and check that. So that way the complexity would also be reduced. Like if I would check for each and every node that the whole subtree is actually smaller, like every node in the subtree is smaller, then the complexity would actually be much more. Like the complexity would be um, n squared, almost n squared. So yeah. Okay, I can't hear you. You Yeah.
Just take an example and try run your solution on that.
Okay, yeah. Let me just. Okay. Okay, so like I have this particular tree. So like I'm not writing the values. I'm just trying to build the intuition. So like I go to the leftmost part of the tree, and from here I will check that its parent's value is actually greater than this leftmost part. If I'm on the right side, at that point of time I'll check if the this node's value is actually greater than the parent's value. Yeah. Okay. So in that way I'll when I will just when I will like in recursion, when I will come back up, so from here when I will return with a value. I'll return with a value, and at this point of time, like when I'm in this stack call, I'll check that I've gone to the left part, and from the left part, the value that is returned is actually less than the node's value. So that way, I can check that the value at the left is actually smaller than that of um, smaller than that of the node's value. And if I'm on the right hand side, like I called for the right hand side, and from right hand side I got a value that is um, greater than the node's value. That means that the this particular subtree this particular subtree is like is a binary search tree, and after that the value of this node will be returned over here in this stack call. At this stack call, I'll check that the value came from the left hand side is actually less than the node's value. If it is, then I'm fine. If it is not, I will simply return false, that it is not a binary search tree. I can't hear you. Okay, 51436. So, hmm, yeah. Okay, so you got what I'm saying, because I can't hear you. I can't hear you, Microsoft.
Oh, kind of. Just dry run your solution on this tree I'm giving to you.
Okay, like what was the tree? 1 5.
Five's left is 1,
Five's left is 1.
five's right is 4,
Five's right is 4. Four's left is
3.
3. Four's right is 6.
Okay,
Yeah.
yes.
So what I'll do is, first of all, I'll go to the leftmost side of like for every node I will do this, but in a recursive way. So I'm at 5. I go to the left hand side of 1, and at 1 I go to the left hand side of 1, that is null. So I've returned null, and that means that it is a root node. So from the root node I will send back the value of that root node.
Okay.
So I have sent 1 on the upper stack call, that is for the value of node 5. So at the stack call of 5, I will check that the value came from the left hand side of the stack call, like the left call that I have made is actually less than the value of node. So if it is, I will continue my work, else I will return false. And then I will go to the right hand side of the node, that is 4. So here it will be a recursive thing, so I have to find the root node. I will find first of all the root node, that will be 3 in my case because I'm doing in order. So I found 3. I will return 3 to the stack call of 4. At the stack call of 4, it will say that okay, it is less than the node's value, that is 4. 3 is less than 4, so it is fine. Then I'll go to the right hand side, that is 6. So 6 is greater than 4, so it is all good. Then I will that confirms that the right subtree of 5 is actually binary search tree. Then I will return 4 to the stack call of 5. So in this particular case, 5 is actually greater than 4. So it will return false because it is not satisfying the condition that the value coming from the right hand side is uh, actually greater than the node's value. So that condition is coming out as false.
You just write down the code for the same.
Yeah. Okay. So I'm doing in order. So it will be in order recursive function. There will be no node root. Okay, so it won't be this. It would be a integer. But like okay, I have to return true or false, right? Okay. So how would I return true or false? Okay, so then let's just take a global variable. Like this is a class of solution, and here is a function of in order, and over here I'm just taking a boolean variable that is true by default, uh, boolean bst bst. So it is true for now. I will just change it to false if I get a condition where the BST is not following. So it is root, and then what I'll do is I'll go to the left side, right? Okay. So int left is equal to in order root dot left. Hmm. In order root dot left, and I have to add base condition as well, like if root dot right and is equal to null, and root dot left is equal to null. That means it is a that means it is a that means what it is, it is a root node. Sorry, not root node, it is a leaf node. Okay, so it is a leaf node, and from the leaf node, what I'll do, I'll just return the value of root node. So root dot val I'll return. Okay. Yeah. Okay, I'll do this, and um, okay, I've returned root dot val. So one will be returned to five. So in that particular example, one will be returned to five, and so it will be in the left. If if left is if left is greater than, sorry,
If left is greater than root value.
yeah, I'm just seeing that how to like break this loop. Like it will be a recursion thing, and there will be some point then my when this condition is coming out to be false, that means my bst variable will be false. And how will I stop this recursion at that point of time? Okay, let's not stop this recursion, let's just yeah, let's not just stop it, let it go through the whole recursion, and at last I will check if bst is false or not. So let's there be a function called check bst check check bst, which will have node root, and in this have I will just call in order. First of all, I'll just call int ans answer is equal to in order in order of root in order of root. So what I'm doing is, I will return -1 over here. I'll return -1 if my tree is not actually a BST. So if if okay, ASN is equal to -1, I'll return false. Else return true. Okay, this is a boolean function. Mhm. Okay, so roots left, and if left is greater than root dot val, then I'm going to do two things. Um, I'm going to do two things. I will just return -1. I'll just return -1, and if it's actually or or left is equal to minus 1. Then I'll just return minus 1 over here. So left part is done. Left part is done. Let's go to the right part. Int right, int right. Um, okay, so int right is equals to in order root dot right, and the same conditions, like if right is actually less than root dot val, I'll do uh, okay, and if right is actually equal to minus 1, at that point of time I'll do just return minus 1. Okay, so the boolean variable, we don't need this boolean variable. Okay, and at last I'll just return the the root's value, root dot val. Yeah, yeah, I think it's done. Hello. कैसा इंटरव्यू रहा है रे? कैसा इंटरव्यू है? हैं? ऐसे होता है इंटरव्यू? माइक ही नहीं ऑन है?
Hmm. Will this work in every test case?
Okay, like if okay, the
First of all,
if root is equal to null,
hmm,
then
right.
yeah, so then I'll return negative value, that is integer dot minimum value, because that value will definitely be smaller than any value. Okay, but I
Right.
came from the, but I came, if I came from left or right, yeah. So that I have
Yes.
to check, right?
Hmm.
Okay. So let's do one thing. Let's add a integer direction, just telling us that we came from left or right. So 0 for left and right for 1, 1 for right. So if root is equal to null, if root is null, if root is null, I will have two conditions, that I came from right or I came from left. So I came from, let's say, if direction is equal to 0, I'll return a minimum value. I'll return integer dot minimum value value. If direction is equal to 1, I'll return integer dot maximum value. Inte- Integer dot max value. Okay, now this will work for every test case. Hmm. Will it work for every test case? At least open up your mic.
I think it will. So we just we are just left with 10 more minutes. So I'm just giving you feedback. Okay.
Okay.
So like in the case of in order iterative traversal, you said I'm going to use stack. Okay.
Yeah.
I don't think if you should do this, you should first think of the question and do something. Um, you should be like, this is my approach, and according to this approach, I should use a data structure, and I think stack would be appropriate for this solution. I
Okay.
think this you should do. For example, like I'm going to use tag. This means like uh, you know the question, you have solved the question before, and this
Yeah.
you already know this. You get my
Okay.
point,
Okay. Yeah.
okay?
Yeah. In order to replicate recursive problems to iterative, we usually use trap.
I
Yeah.
know, I know. But I'm not just telling you about this question, I'm telling you it for every question. In general,
Okay.
I'm telling you, okay?
Okay.
Just go through the approach first, explain your approach first, and then say, according to my approach, I think this data structure will help me, okay?
Okay.
I'm not telling you
Yeah.
only for this particular question.
Yeah.
Second thing is, don't start with the code.
Okay. No, like
Share, explain your approach to the interview, and then ask for the interview if I should write, or if I should start writing the code.
okay. Like I
Um,
was not writing the code at first. I've written the code of the recursion one, right? So I thought that you just wanted me to convert it to iterative one, right? So over here, I was using pen and paper and explaining everything, but at your end, you were not replying back.
okay.
Okay,
Okay.
yeah,
But it was a pretty good interview. Uh, all these questions I have solved by myself also,
yeah,
but to every solution you have given me another approach of solving the question.
okay,
Okay,
yeah,
so if I just go to the first question first.
yeah,
So when I first tried this question, I went with your approach only.
okay,
Okay, I went. What should I dry run your solution? Okay, so I'm not saying if this will work or not, but it seems fine. Okay,
okay,
um, what would be a better, I would say, better approach of solving this question would be find the middle by fast and slow pointer. Okay,
okay,
then make two list out of one.
okay,
Okay, you get it. List one would be one, two, three,
okay, yeah,
then
yeah,
null, then four, five, six.
yeah,
List two will be four, five, six. Then you reverse the second linked list.
yeah. So,
Okay,
yeah,
then you go ahead. This will be a simpler approach.
yeah,
Then if you then in order wala question was fine. Just go through the okay. Then again in the third question,
yeah,
I want you to write the similar code in some code editor or lead code or GFG, wherever you want. And I want you to show me if this will work.
okay, sure.
Okay, this seems fine, but see, you have increased the understanding complexity of the
All
question.
right, yeah,
So, right? You agree to this? And I want you to simplify this code.
okay,
It should be readable.
okay,
If
yeah,
I'm looking at something, um, I should understand what are you doing and why you are doing this.
okay,
Right. That's all
okay,
I
yeah.
would say.
Let's make it readable.
Readable in not terms of indentation.
Yeah,
It should also make sense to me.
okay, like so, if
At first,
yeah,
if I go ahead, if I haven't heard of your approach, I will be confused. Why are you taking zero and ones? What is the dir? And
yeah,
fine, your question is this is fine. First, you show me if this will work.
okay,
Okay.
okay, yeah,
Also, you have missed one condition here. If I give you a three like two, two, and two,
uh,
three nodes,
three,
two's left is two, two's right is two.
okay.
Will this work in this condition?
So okay, okay. So I'm just doing this. So my root is two, right? So yeah. So at that point of time, neither of these two conditions is true. So I'll go to the left and do the in-order traversal for that. And okay, and I'll just return the root's value, right? I'll return the root's value. That will be 2. Yeah. Okay. So it is equal to, yeah. Yeah. So I'll just have this thing at the last, that if root dot if root dot val is equal to left, or root dot right is equal to uh, sorry, not root dot right, root dot val is equal to right. So I'll return -1. Yeah.
Also, dry run the question, dry run this solution, code this in or lead code or GFG
Okay.
and
Okay.
show me the result.
Yeah. Like
Okay.
I could have just changed here equal to. I've just added equal to
Yes.
over here, and
Right.
that would also work.
Right.
Yeah. Okay. I'll submit it on any platform and let you know.
Yes.
Okay.
So thank you.
Okay. Okay.
Now.
Bye. Bye. Thank you. Okay. Okay. अभी भी चल रही है मीटिंग. Okay. I think you liked it. इसे कोई देख तो रहा नहीं है, but still अगर कोई देखेगा, so please consider subscribing. Okay. Okay. See you later. Bye.